You know, some differential equations look like these impossible puzzles, right? The variables are so tangled up, there's just no way to separate them. But for a very special type, the homogeneous equation, there's this incredibly elegant trick that unlocks the entire thing. So today, let's walk through how to find and use that key step by step.
So picture this. You're staring down a differential equation. You're trying your best to separate the variables, get all your x's on one side and all your y's on the other, but they are just hopelessly stuck together. It feels like a locked box. You know the answer's inside, but you just don't have the key. Well, it turns out, for a special class of these equations, there is a key. But first, we have to learn how to recognize the lock.
So how do we identify this specific type of puzzle? Well, there's a test we can run, a really specific check, to make sure we're actually dealing with a homogeneous equation. And this whole test, this crucial first step, it all boils down to a property called the homogeneous function. Okay, so here's the formal definition, and this is really the heart of our test. A function is called homogeneous if, when you replace every single x with tx and every y with ty, you can neatly factor out that t raised to some single power. That power, we call it alpha here, that's the degree. Now, that probably sounds a little abstract, so let's make it way more concrete with a quick example. Okay, check out this function. F of xy equals x squared plus y squared minus xy. Let's run the test. We're going to substitute tx for x and ty for y. What do we get? We get t squared x squared plus t squared y squared minus t squared xy. Now, do you see it? That t squared shows up in every single term. That means we can pull it right out front, leaving our original function perfectly intact. And that's the proof. This function is homogeneous of degree 2. Now, let's look at the flip side. Let's see a function that fails the test, like this one, x squared minus y squared plus x minus y. When we do the same substitution, we get a t squared from the first two terms, sure, but we only get a single t from the last two. And because we can't factor out one single common power of t from the whole thing, it is not homogeneous. So the test is really that simple. Either t factors out cleanly, or it doesn't.
So how does this all relate back to our big differential equation? Well, an equation in that classic m dx plus n dy equals 0 form is considered homogeneous only if both m and n are homogeneous functions, and this is the important part, of the exact same degree. That shared degree is the secret weakness. It's what makes the whole puzzle solvable.
Okay, so now we can identify the lock. It's time to introduce the key. And honestly, it's a magic substitution. The first time you see it, it might seem like it comes out of nowhere, but trust me, it is specifically designed to pop this puzzle wide open.
And here it is. This is the master key. Y equals u times x. This simple-looking substitution is literally the hero of our story. It's the one move that takes a completely tangled, non-separable equation and transforms it into something familiar and, most importantly, something we can actually solve.
But why does it work? It's not really magic, of course. It's just clever algebra. Look at the steps right here. Because m and n have the same degree, that alpha, when we substitute ux in for y, we can factor out x to the power of alpha from both terms. You can see it right there. This becomes a common factor for the entire equation, which means we can just divide it out. And just like that, it's gone. What we're left with is a new equation with just u and x. And here's the kicker. It is guaranteed to be separable. So here's our game plan, our roadmap to the solution. Step 1, confirm it's homogeneous. You got to do this first. Step 2, unleash our key, y equals uv. Step 3, simplify and let those terms cancel out. Step 4, solve the new, much friendlier separable equation. And finally, step 5, substitute back to get our answer in terms of the original x and y.
All right, theory is great and all, but let's make this real. We're now going to take everything we've just talked about and apply it to a concrete example, from start to finish. Let's do this.
Okay, here's our challenge problem. And at first glance, yeah, it looks pretty messy. But let's run our test. The m part, that's x squared plus y squared. That's homogeneous of degree 2. Now the n part, x squared minus xy, that's also homogeneous of degree 2. Ding, 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 we've got a match. This is our kind of puzzle.
All right, time for the key. We're going to let y equal ux. And don't forget the other part of this. We also have to substitute for dy. Using the product rule, that becomes u dx plus x du. So now we plug both of these into our original equation, replacing every single y and the dy.
And here it is. This is the magic moment. After we do the substitution and simplify a bit, the x squared term factors out of absolutely everything and just cancels out, exactly like the theory predicted it would. And look what we're left with. You see it highlighted in the box? That is a separable equation. The lock is open. Now we can finally get all of our x terms to one side and all of our u terms to the other. From here on out, it's pretty much standard calculus. We integrate both sides of our new separable equation. And as you can see from the work here, this one involves a bit of algebra, leads to some natural logs, but the final crucial step is to resubstitute. Since our key was y equals ux, that means u is y over x. We replace every u with y over x, and after a little more tidying up, we arrive at the final solution to our original problem.
So let's just step back for a second and think about what we just did. We took a problem that looked really intimidating, something that seemed stuck, and with the right approach, we turned it into something totally straightforward. So what's the big takeaway here? Well, first, when an equation seems hopelessly tangled, look for a hidden structure, like homogeneity. Second, always use that t substitution to diagnose it, don't just guess. And third, remember that master key, y equals ux. It isn't just a random trick, it's a specific tool designed to transform a complex lock into a simple puzzle that you already know how to solve. And that kind of leaves us with a final thought, doesn't it? This whole process, identifying a special structure and then using a specific tool to simplify it, that's a theme you see all over mathematics. It makes you wonder, what other seemingly impossible puzzles are out there, just waiting for us to find the right key?